So as we begin Module 9, we're taking a look at the topic of transformations of stress and strain. Now within this module, we're going to examine methods for determining maximum stresses and strains at any point in a structure. We're also going to be looking at the stress conditions necessary to cause failure. So a couple objectives within this module. We're going to be taking a look at applying stress transformation equations to plane stress situations in order to determine any stress component at a point. Looking at application of the alternative Moore's circle approach to perform plane stress transformations, using transformation techniques to identify key components of stress, such as our principal stresses, looking at the extended Moore's circle analysis to examine 3D states of stress, examine theories of failure for ductile and brittle materials, analyze plane stress states in thin-walled pressure vessels, and then finally we're going to look at the extended Moore's circle analysis to examine transformations of strain. So this relates back to our textbook, to Chapter 7. So we're going to break this module into two sections, 9.1 and 9.2. For Module 9.1, this relates to Chapter 7, Sections 1 and 2. For Module 9.2, this relates to Chapter 7, Sections 3 and 4. So as we get into Module 9.1, this is our first section for this module. We're going to take a look at the topic of transformations of stress and strain and Moore's circle. So relating back to our textbook, this is section 7.1 and 7.2, where 7.1 is a transformation of plane stress, and 7.2 is Moore's circle for plane stress. Activities within this module, going over the theory for the above topics, looking at some of the key equations, going through some practical applications, and then getting into some actual problem solving as well. So as we jump into this module, let's go through a little bit of an introduction here. So the most general state of stress at a point may be represented by 6 different components. So if we take a look at these 6 different components, we can see we can break these into our normal and our shear stresses right there. Now if we're talking about our normal stresses, we have our sigma x, sigma y, and sigma z. And for our shearing, similarly, we have our tau xy, tau yz, and tau zx right there. So now let's break these down for a minute and take a look at these relative to our diagram over here. Now one thing we can notice about this diagram over here is that we have a standard coordinate system. There's our x component, y component, and z component for our coordinate system right there. So if we look at this right here, if we take and use our right hand rule and we curl our x-axis towards our y-axis, then we have our z coming out right here. So again, if we do our right hand rule right here, we can see that our z does come out like this right here. So this is something that's important. We want to make sure we have our sign convention correct, and we also want to make sure that we've clearly labeled our coordinate system, because when we start trying to look at all these different 6 components, again, these are reference to that given coordinate system. So we need to understand what those are. So let's take a look right here in our x direction. So we look at our axis right here. We have our sigma x, so there's our sigma x right there. Then our y-axis, there's our sigma y right there, and on our z-axis, so coming out here, there's our sigma z right there. Now, what we want to take a look at now is our shearing stresses and understand what these indices mean right here. So if we have our tau xy, there's our tau xy right here. So we can see this is going in our xy direction right there. Then we have our tau yz. So our tau yz right there. So now we can see this has a component right here in our y and z direction right there. And now we have down here our tau zx right there. This is our tau zx right there. So we can see there's our tau zx right there. Now we can notice here, if we take a look here, our tau xy is equal to tau yx, and our tau yz is equal to tau zy, and our tau zx is equal to tau xz right there. And we can notice that if we look back at this diagram here as well and see both of those. So there's our tau yx, tau xy. Then we can take a look over here, tau zx, tau xz right there. And then we also have our tau zy right there. And we can see there's our tau yz right there. Now another thing we want to consider right here is maybe that standard x, y, z coordinate for this 3-dimensional case right here is not always the best for our application, whatever that may be. So sometimes we may need to rotate that axis to a slightly different. We can see our prime. So there's our x prime, y prime, and z prime axes right here. So we can notice here is that same state of stress is now going to be represented by a different set of components if the axes are rotated. So you can see this, our primes are all noted right here as well. So now the first part of this module and the first part of this chapter are going to be concerned with how the components of stress are going to be transformed under a rotation of the coordinate axis. This is something that we're going to need to understand how we're going to do that rotation, how it's going to affect those components. Whereas the second part of the chapter is then going to be devoted to a similar analysis, but now we're taking a look at the transformation of the components of our strain. So as we continue on with our introduction here, I want to now take a look at plane stress. So what is plane stress? Well, plane stress is a state of stress in which two faces of the cubic element, so two of the different faces of the cubic element, are going to be free of stress. So let's take a look at this illustrated example over here on the left right there. We have non-zero stress components for the state of plane stress right here. So you can see now we're just dealing with our sigma y and our sigma x right there, and are dealing with our tau xy right there. So there's our tau xy, tau yx, which those two are going to be equal to each other right there. But that's it. There is no sigma z, and there's neither one of those shear stresses right there. So we can see now from our element right here that our sigma z, which would normally coming out of this face like that, is now equal to 0. Our tau zy and our tau yz are also both equal to 0 right there. So therefore now we have, by that definition right there, two faces of the cube element are going to be free of stress. So now rather than a cube, let's take a look here at a thin plate. So this is an example of plane stress where we have a thin plate subjected to an only in-plane loads right there. So the state of stress occurs in a thin plate subjected to forces acting in the midplane of the plate. So we can see all these forces right here are all acting right there. If you look at that, right at the midplane of the plate. So our F1, we can see right at the midplane right there, 2, 3, 4, 5, and 6. No matter what direction they're in, we can see that all of these are right at the midplane of that thin plate right there. Now, the state of plane stress can also occur on a free surface of a structural element or machine component, which is any point on the surface that's not subjected to an external force down here. So we can take a look down here at this example for plane stress right here. We have that free surface of a structural component right there. So this right here, if we think about this cantilevered beam right here, we have this cylinder, this rod coming out fixed at this end over here. This right here is going to be what we refer to as our free surface. So then we can see we have this F1 and F2 acting at that right there. So this is an example right here. We have that plane stress occurring on the surface, free surface of a structural element. So now let's consider the case here where we're looking at the transformation of this plane stress that we've just been discussing right here. So for this here, to look at transformation, let's take a simple shape right here. So let's consider this prismatic element right here. So we have conditions for equilibrium right here for our prismatic element, and the faces are perpendicular to our x, y, and our x prime axes. So we can take a look at this element right over here in part A of our figure off to the left here, and we can see, okay, there's our x-axis right here, there's our y-axis right there. Now we can see here our x prime and our y prime axes right here. So we can see this angle as we rotate here, as it's transformed from our x to our x prime, we have this angle of theta right there. Now this is going to be the same theta as if we were to look at the front of this triangle right here. That's our same theta right there as well. And why is this the case? Well, if you take a look and see, what we're doing is we're rotating our standard XY coordinate right here by that angle and making it flush up against the face of this element, this 3D prismatic element right there. So it's going right up along there. So that's why this angle is equal to this angle is equal to this angle right there. So let's take a little bit closer look at that trig right there. So if we can see, we have this basic right triangle here. So if we take this face right here like this, what we can see is there's our angle theta right there. Opposite over hypotenuse, there's our sine of theta right there. Adjacent over hypotenuse, there's our cosine of theta right there. Now we're looking at here, if this is our delta A, is this whole flat plane right there. So our area right there is our delta A. So that's our delta A right there. So I've kind of broken this plane off into 2D right there. So you can see that front surface right there, that's our delta A. Now on the bottom of this right here, of this prismatic member right there, we have this delta A times the sine of theta, because again, it's associated with this right here, and this length right here is the same for all of these. So that length going across right there stays the same for all those there. So this is just going to be our delta A times that sine of theta there. And the same thing for now this back face right here. The back face right here is going to have this delta A times the cosine of theta, because again, that width right there stays the same for all of those right there, and same across the bottom if we were to draw that out there. That width stays the same there for that back face that we're looking at now. So this would just be our delta A times the cosine of theta there. So this is just to give us a little visual on how we come up with these relationships for those different faces. So now let's go back and actually consider those conditions for equilibrium right here of a prismatic element with faces perpendicular to the x, y, and x prime axes right there. So we can take a look at that and we say, okay, well, this is our x-axis right here. What's perpendicular to that? Well, those are forces right there and there. Then we can say our y. Well, we have this force here and this force here. We have our x prime right here, which is going to be this force here. And we can see now that this y prime right here, we have this tau x prime y prime delta a right there for that force right there. And you can see that that's going to have components in both its x and its y directions right there. So now the question is, do we look at this in our standard xy coordinate system? Or do we look at this in this new y prime, x prime coordinate system? So we've decided to go ahead now and look at this in our x prime, y prime coordinate system. So when we do our summation of forces and our equilibrium equations right here, we're going to do this with the summation of forces in our x prime direction and the summation of forces in our y prime direction. So now what I've done over here is I've kind of drawn out this little triangle right there, showing, okay, there's our theta, I've blown it up a little bit right there. There's our x prime going up, our ramp right there, and our y prime perpendicular to that ramp right there, just to help us with a little bit of trig as we're going through and need to break things down in terms of their components. So we can see, let's just start with our x prime direction first. That's the easiest right there. In our x prime direction, summation of forces in this x prime direction are equal to 0. That's our equilibrium right there. Well, the only force acting purely in that is this guy right here, our sigma x prime delta a. So we write that down. I've color coordinated this here. So in this light green, we have our sigma x prime delta a right there. It corresponds to that there. What else is acting in that axis, our x prime axis now? Well, we can see, well, all of these are actually going to have a component that right here. So all of these right there are going to have components in our x prime axis right there, because these are acting purely in our y or purely in our x, but we can see our x prime has components of both our y and our x right there. So let's just go down through. So we go to our blue one first here. So this is acting purely in our negative x direction, which is going to have a component in our x prime direction. So we can go back over here to our trig triangle if we want to double check, make sure we break things down correctly right there to get it into our new coordinate system. So we look at that there and we say, okay, well, this is going to be our sigma x times delta a cosine x, which is that force right there that we found from our previous trig right there. And now we can take that and we can say, well, if we break that down to our x prime component of that, that's going to be times the cosine of theta right there. So that's where we get this relationship there for our second term in our x prime direction. Then we can take this component in our yellow circle here, our tau xy times our delta a cosine x, which is acting purely in our negative y direction. Well, again, that's going to have a component in both our x prime and our y prime right there. So we break that down, that's going to be tau xy, delta a cosine of theta for our force, times, now to break into its components, it's sine of theta. So again, double check your trig triangle and make sure that's correct. Then we go over here and we say, well, our underlined pink section right here, this right here is acting purely in our negative y, which is a delta y times sigma y times delta a sine theta right there. Break that down in terms of its delta x component, and that's times the sine y right there. Then we can go on here to our last one, underlined in our purple right here, our tau xy times our delta a sine of theta. Break that down in terms of its delta x, or x prime components right there. So now we have our tau xy, our tau xy times our delta a times the sine of theta times the cosine of theta there. So that deals with just our summation of force or equilibrium equations in our x prime condition. Now we want to do the same thing for our y prime. So where is our y prime on this one here? Well, this is our y prime direction right there, coming off perpendicular to our ramp right there. And we can see there's our y prime right there, related back to our 3D prismatic element right there. So now what we can do is we can take and say, okay, what forces are acting in my y prime direction? And the equilibrium, those are going to be equal to 0. So in our y prime direction, we purely, in our dark green right here, we have our tau x prime, y prime, delta a right there for us. So we write that right down. Now we do have a y prime component of this in our light blue circle right here, our delta x times, sigma x times delta a cosine of theta. So we take that there. Now, rather than being times the cosine of theta to get it in our x prime, it's times the sine of theta to get it in our y prime. So then we go down to our next one here, our tau xy times delta a cosine of theta right there. Well, again, we now multiply this by now a cosine of theta right there to get that in terms of its y prime direction right there. Then we go down to our pink underline, or sigma y times our delta a sine of theta right there. Multiply that by the cosine of theta to get that in our delta y, our y prime direction right there. And then we go to our purple right here, our tau xy right there, times our delta a sine of theta, tau xy delta a sine of theta. Multiply that by a sine of theta right now to get that one into our y prime direction. So that is why it's really important that we want to clearly draw out and understand our diagrams right there. And if this is too cluttered right there, draw a separate one for your x, a separate one for your y right there, for your free body diagram. Simplify it down, look at it in 2D if you need to. Break out your trig triangles if you need to. Make sure you get your sines and your cosines correct. This is a lot going on here, a lot of different forces that we need to break down in terms of this new coordinate system, our x prime, y prime coordinate system. So taking the time, looking at geometry, going through your trig, separating things out, dealing with each thing separately is going to help a lot with this. So now we do have expressions for our equilibrium equations for our x prime direction and our y prime direction. So now that we've had these expressions that we've derived looking at that free body diagram, doing our equilibrium equations for our summation of forces in our x prime direction, summation of forces in our y prime direction, we can now go through these and we can rearrange these and solve these for our variables of interest right here. So we can get an expression by rearranging that to get our sigma x prime, our sigma y prime, and our tau x prime y prime right there. And we can relate those back to our diagrams right there. So this is something that's also important to do, is understand what they're asking you to solve for in the problem, or if you need a piece of something to plug into something else. Simplifying and rearranging these equations is not always the easiest thing to do, but take your time, go through it, and again, deal with them piece by piece, individual parts at a time. Pay attention to sign convention, pay attention to your trig, and in some cases here, pay attention to trig identity if you can use things like that as well. And as you're going through those, you can reduce and simplify things down. Now, is this always necessary? No. Sometimes this is an extra step where you could have easily just gone back into the original equations and plugged in known values if those were given to you, and that'd be a lot easier than trying to figure out trig identities and simplifying and rearranging. So pay attention to what they ask for and what they give you, which again relates back to that initial setup page that we have in our problems, where we have all the information they give us, everything they've asked us to solve, our assumptions, and then from there we can decide, oh, okay, this is already given to me, I can just plug that in, or this is not what they wanted, this is what they wanted, so I can rearrange that way. Now I just wanted to include a slide here with a little review of our trigonometric relations right here. This relates back to our textbook as well. So if we recall these trig relationships right here, we have this relationship that the sine of 2 theta is equal to 2 times the sine of theta times the cosine of theta. The cosine of 2 theta is equal to our cosine squared theta minus sine squared theta. Our cosine squared theta is equal to 1 plus the cosine of 2 theta over 2. And our sine squared of theta is equal to 1 minus our cosine of 2 theta all over 2. So let's take a minute to take a look now at our principal stresses right here. So we can take those previous equations right there and combine them in order to get our parametric equations for a circle right there. So we have this relationship right here where we now have our sigma x prime minus our sigma average squared plus our tau x prime y prime squared is equal to r squared. Now let's relate this to a diagram right here. So what is our sigma x prime minus our sigma average squared? Well, there's our sigma x prime right there. So that goes all the way from our origin out here to this point that we're interested in here on the circle right here, this m right there. Now this is minus our sigma average. So if we take a look at our sigma average right here, this goes to the center point of the circle from that initial start point right there. So what we're left with is this distance along the bottom right here like that. So that's the distance that we're left with right there. So that squared plus now our tau x prime y prime squared. Well, our tau x prime y prime squared is this right here. So this distance right there, we can see that's our tau x prime y prime squared, going from there to our up to our point M right there. So if we take our, and essentially a Pythagorean theorem right here, our x squared plus our y squared, we get our hypotenuse squared over here, r squared right there. So a squared plus b squared is equal to c squared is where this relationship comes from. Where the tricky part right here is that a squared right there. If we get this distance right here, we need to say this is our sigma x prime minus our sigma average right there. Where in general our definition for our average sigma right here is our sigma x plus our sigma y all divided by 2. So adding those two together and divide by 2 gives us that average value right there. Now what we could also do is we could rearrange this and solve for our r value right there. So our r value is equal to the square root of, now there's our sigma average right there, definition right there, squared minus our tau x y squared right there. So this is equal to the square root of that value squared plus our tau x y squared right there in order to get our r value right there. So continuing on to the topic of our principal stresses right here, one thing I want to note is the principal stresses occur in the principal planes of stress with zero shearing stresses. So let's take a look at our diagram over here for our principal stresses, and we can see along our x prime and our y prime axis, this is where we have our sigma max and our sigma min right there. So the max is occurring along this right here for our x prime axis, and our minimum stress here is occurring along our y prime axis right there. And we know that there are no shearing stresses in this diagram right here for our principal stresses. So our general equation for calculating our max and min value for our stress right here is equal to, now we have that average right there, our sigma x plus our sigma y over 2. Now this is where it's max or min is because we have this plus or minus right there, times our square root. Now we have that same here, the average again right there, which is our sigma x minus sigma y all over 2 squared, minus our tau x y squared right there. So we can rearrange this right here. And what we see now, this is also equal to this tangent of 2 times our theta p. Well, what is theta p right here? If we go back to our diagram right here, this comes from our x-axis, and notice this arrow goes all the way up to our y prime axis right here. So that is that theta p going past the 90 degrees between x and y up to our new y prime axis from our x-axis right there. So the tangent of 2 times that angle is equal to 2 times our tau xy all over our sigma x minus sigma y. Now, a thing to note down here, this defines 2 angles separated by 90 degrees like we just saw in our diagram. So now I want to take a look at our maximum shearing stress now. So similarly, we have the same type of diagram that we see over here in this figure here. We have a circular relationship for transformed stresses right there. And we also have down here our maximum shearing stress down here, similar to what we saw in our previous slides right there, but now looking at our maximum shearing stress. So the thing to note right here is that our maximum shearing stress is going to occur for our sigma x prime is equal to our sigma average right there. So if we look back at our diagram for that right there, this is our sigma x prime, and this is our sigma average right there. So how would these be equal to each other? So that's what we got to think about. What relationship do we need for those two to be equal to each other? So if we think about that right there, if the circle doesn't move at all right there, in order for our sigma x prime to equal to our sigma average right here, if we take this sigma x prime right there and we want it to be equal to our sigma average right there, then we would move this m back to this position now where it's at D. In that case there, then we would have our sigma x prime equal to our sigma average right there, and we'd have this right at the top of our circle there. So our relationship equation here says our tau max, or our maximum shearing stress right there, is equal to R, which is equal to the square root of that average again right there, our sigma x minus sigma y all over 2 squared, plus our tau xy squared right there. So now going down below to this figure here, we'll take a look at our element right here. Now we can see we have this angle here, our theta sub s term right there. And that theta sub s term is our angle right there that is between our x-axis right here and our x prime axis. And we can also see that our sigma prime right here lies on our x prime axis. And we can also see that our tau max right here, that maximum shearing stress, occurs along that x prime axis as well. Now we can note that tangent of 2 times our theta s, that same angle that we're talking about there, which is the angle between our x and our x prime axis right there, is going to be equal to a negative value now for our sigma x minus our sigma y right there, divided by our 2 times our tau xy right there. So that's our relationship there between that angle and our shear and our normal stresses right there. We can note now this defines 2 angles separated by 90 degrees and offset from our theta p, from our previous slide right there, by our principles, by 45 degrees right there. So now we can see we have this relationship here giving this equation that our sigma prime is equal to our sigma average, which is equal to now, our sigma average, as we recall, is that sigma x plus sigma y all over 2. Which also brings us back up to this relationship that we saw at the beginning here, where we said that our maximum shearing stress occurs where our sigma x prime is equal to our sigma average. And that's exactly what it says. Sigma x prime is equal to our sigma average. So now let's apply some of that theory and governing equations we just took a look at here to an example problem. So in this problem here, let's take a look at concept application 7.1. So we have here, we can see in this diagram here, a plane stress element. So now for this element right here, they tell us that for this plane stress shown, they want us to determine 3 different things. So they want us to determine in part A, the principal planes, part B, the principal stresses, and then in part C, the maximum shearing stress and the corresponding normal stresses in there. So technically we have 4 things that we're going to be solving for within this here. So you can go up, look at our diagram up here. We can see they've labeled this here as our 10 megapascals, 40 megapascals, and our 50 megapascals, all right there from this plane stress element. So as we think about this, what they've given us is not much. Just have a diagram and a little bit of a statement here. And they've asked us to solve for 3 different things. So let's think about a procedure for analysis as we go through solving this problem right here. So our solution right here, what we first want to do, think about this, is we want to find the element orientation right here. So if we find the orientation for our principal stresses, and we can do this from this relationship that we've seen before earlier in this module and back in our textbook right here. We have the tangent of 2 times our theta p is equal to 2 times our tau, our shear stress right here, xy, divided by our sigma x minus our sigma y right there. So that'll be the first part of our procedure for analysis, is utilizing that governing equation to find our element orientation right there. By orientation, we can find those angles right there. So next what we want to do is determine the principal stresses. That's the second part right here. Once we found the planes, then we find our stresses right there. And we can do this from this relationship equation that we've seen before as well. So this is our sigma max, sigma min. We can find both those. Again, this is plus or minus right there. And this is sigma x plus our sigma y over 2 right there, which again is our average value for our stress right there. Plus or minus now the square root of our sigma x minus sigma y all over 2 squared plus now our tau xy, our shear stress in the xy squared right there. So that's our governing equation we're going to use to find our principal stresses, our sigma max and our sigma min right there. Now last, we want to find our maximum shearing stress. That goes back to part C over here, and we can use this governing equation here to find that there, where we have now our tau max is equal to the square root of our sigma x minus sigma y squared, sigma y over 2, all quantity squared, plus our tau xy squared. And we also have the relationship here. We recall this for when we're calculating our maximum shearing stress right there, that our sigma prime is equal to our sigma average right there, which is our sigma x plus sigma y all over 2. So now that we've had the opportunity to read through that problem statement and take a look at our initial given diagram, we have all the information we need to create our setup page. So if we were solving this problem out by hand, we'd then create that setup page. We take all that information from the diagram and problem statement and write out everything that's given to us in one section. Then below that, write out everything that asks us to solve for. And then as well, we want to include any given coordinate systems, any assumptions we're making as well. And this will be the page that we can reference back to and utilize that information to determine what is our governing equation. So once we have all that with our setup page and we can reference back to it, we then want to take a look at that procedure for analysis that we went through. And we'll say, okay, let's deal with just part A of our problem right here from our setup page and our problem statement, looking for our principal planes. So we can go to procedure for analysis as we get our solution right here and we say, okay, and this here, our first step is going to be to find the element orientation for the principal stresses. Now we can do this from our governing equation. So if we go back to our textbook, this is equation number 7.12 that we're utilizing here. We saw this earlier in the module here. So this is the fact that we have the tangent of 2 times our theta p right there, where this is our theta p, right down there, is equal to, now in our case here, we have 2 times our shear stress right here, tau xy, all divided by x minus y right there. So let's plug in our known values for this right here. Well, we can see that our shear stress, so if 2 times our shear stress right there, well, this is our shear stress right there, that 40 MPa, which is right from our given diagram. And again, this is something that on our setup page we would have wrote out tau xy is equal to 40 MPa. So we could plug straight into this here and wouldn't have to necessarily reference back to just the diagram. So that's why having that setup page is really nice, because you've already clearly labeled everything. And again, in that given section, there's 4 things we want to include: the variable name, the numerical value, the units that you're using, and how it relates to your problem right there. So in this case here, the variable name is our tau xy. How it relates back to our problem is our shear stress. Our numerical value is 40, and our units are MPa right there. So all those things that we'd normally include in the given section on our setup page right there. So we plug that in for our tau xy. Then we can also see we have our sigma x minus our sigma y. Pay attention to your sign convention right here. Our sigma x right here, well, that is our 50 right there. There's our 50 MPa right there. And our sigma y right here is a negative 10. So this comes from 10 right here, where we should have our coordinate system drawn out for this problem here. We have positive x to the right, and we have a positive y going up right there. So those are all the values that we can plug straight into that equation 7.12. And from that right there, we find that our tangent of 2 times our theta p right there, theta sub p right there is equal to 1.333. So then we can say, well, let's convert that from radians to degrees right there. So 2 times our theta sub p is equal to either 53.1 degrees or 233.1 degrees right there. Well, then we can go and divide both sides by 2. So our theta sub p is equal to either 26.6 or 116.6 degrees right there. So we come down here, if it's below 90, as we see down here in this D right here, we have our plane stress element oriented in the principal directions right there. Then this is our theta p that now we can plug in that numeric value for right there. Now, another thing to note is our diagrams as well, as we talked about that setup page. So if we're doing something like this, yes, this may have been given in the problem statement, but redrawing this out, using this as your free body diagram there, and as you see right there, we've labeled this. This is our plane stress element right there. We have our coordinate system that we drew in right there with what's positive x, what's positive y, and then see down below here, even if we have this on our setup page, this is nice to redraw, do this right here, so we have these clearly available for us as we're doing out our solution page as well. So yes, we can reference back and flip back to that setup page, but having these clearly labeled out, again, as we're plugging into these governing equations right here, makes it really easy for us as we're solving. So now we've gone ahead and completed our solution for part A. We can go back to our setup page, back to our original problem statement, say, okay, what's next? Next is part B. We need to solve for our principal stresses right here. So we go back to our procedure for analysis. For this step, looking for our principal stresses, what we're going to do is determine the principal stresses from our governing equation, which is shown here for our sigma max min right here, which relates back in our textbook to equation 7.14. So now you can see I've redrawn out that same plane stress element up here. So now I can go through, let's start plugging in with our known values, which I can flip back to my setup page to get right there for this governing equation. So my sigma max min is equal to my sigma x plus my sigma y, all divided by 2 right there, plus or minus, now that's where we're going to get two values for this right here for max and min, plus or minus the square root of that sigma x minus sigma y over 2 squared plus my tau xy squared. Now all those values we have, again I can have these right on my setup page, but I'd like to redraw them out on my solution page as well, so I have them right there. There's my variable name, there's my numerical value, and there is my units right there, so I can plug those straight into this governing equation 7.14 up here. So I can plug that in, my sigma x, I can come down here as 50 megapascals, going back to my diagram, there it is right there, my sigma in x direction. I can draw out my coordinate system where x is positive to the right, and my y is positive going up right there. So I'm plugging my sigma x to 50 megapascals, my sigma y, which is right here, my negative 10, that's because it's 10 going down this way in the negative y direction right there, all divided by 2, plus or minus the square root of my sigma x again, that 50 megapascals right there, minus sigma y, so it's minus a minus, so it's a double negative there, pay attention to your sign convention right there, all divided by 2, but that entire quantity is squared, plus my tau xy squared right there, where my tau xy is my 40 megapascals, and I can see that right there, going in my positive x direction, that's a positive value right there. So this reduces down when I do this out here of 20 plus or minus the square root of 30 squared plus 40 squared. Do my math out right there, and I have that plus or minus gives me my max and my min. I find out now that I have a sigma max is equal to 70 megapascals and a sigma min right here of negative 30 megapascals. Double check your unit analysis out there. Then we can draw that in down here in our plane stress element. Again, this is oriented in our principal directions right here. We draw that out there and we can see, well, this value right here, that's our sigma max, and that we just found to be 70 megapascals, and then our sigma min going down in this direction right here is 30 megapascals right there. So now we've completed our solution to parts A and parts B for this problem. So go back to our setup page or our original problem statement, realize there is a part C. And part C actually has two parts to it. We want to find our maximum shearing stress and the corresponding normal stress right there. So we can take a look at our procedure for analysis and realize, well, how we're going to do this to calculate our maximum shearing stress. We're going to utilize our governing equation 7.16 from our textbook right there, where we have that our tau max, or our maximum shearing stress, is equal to the square root of our sigma x minus sigma y all over 2, quantity squared, plus our tau xy squared there. So we can come back over here. We have our diagram here. Draw it again, our coordinate system, positive x going to the right, and we have our positive y going up right there. And we read it out for our plane stress elements right here, each of the variables and our numeric values and units right here. So our sigma x right there is 50 megapascals positive. Our sigma y right here is 10 megapascals negative. And our tau xy, our shear right here, is 40 megapascals going in the positive x direction there. So we can come back over to our governing equation, 7.16, plug in our tau max, or our max shearing stress, is equal to the square root of our sigma x, which is 50, minus our sigma y, so minus a negative, pay attention to sign convention right there, plug that in, minus negative 10 right there, all divided by 2 squared, ends up being a 30 squared. And our tau xy we see over here is 40, so that's a 40 squared right there. Take the square root of the sum of both of those. And what we end up with is that our tau max, or our maximum shearing stress, is equal to 50 megapascals. Now we have this relationship here that our theta s is equal to our theta p minus 45. So we have our theta p previously right there. We can plug that in, and we say theta p minus that 45, which comes from our relationships of equation 7.12 and 7.15 in our textbook right there, that theta s is equal to theta p minus 45. I find out that my theta s, again, we have two values for my theta p, so my theta s is either negative 18.4 degrees or 71.6 degrees right there. So we come back over here, and there's our theta s is equal to negative 18.6 degrees as we show our plane stress element right here. And from this right now, we can then calculate as well our corresponding normal stress. So that was the second part of this problem here, to calculate the corresponding normal stress. So our sigma right here, prime, from equation 7.17 in our textbook, is equal to our average stress right there, which is our definition again from that equation, sigma x plus sigma y over 2, where I have a sigma x of 50, sigma y of negative 10. So 50 minus 10 divided by 2 is 40 divided by 2. So our corresponding normal stress right here, our sigma prime right there, is equal to 20 megapascals. So now let's take a look at Moore's circle for plane stress right here and look at how we can actually create this from the information we're given in a plane stress element. So with this physical significance of Moore's circle for plane stress established, it may be applied with some simple geometric considerations. So critical values are estimated graphically or calculated. So that's something to think about right there. If we obtain these graphically, this will be an estimated value and not necessarily an exact value there. So now, if we have a known state of plane stress right there, so we have our sigma x, our sigma y, and our tau xy, we can plot the points x and y and construct the circle centered at C. So this is how we're going to create our Moore circle from that information. So we come back to part A where we have our plane stress element and the orientation of our principal planes right there. So we can see over here, here's our stress element right there that we've seen before. There now we have our sigma y going up in our positive y direction, our sigma x going over in our positive x direction. We have our shearing stress right there, our tau xy. Then we can see, we can rotate it, translate about this theta sub p right there. And we now have this relationship we see here for this element right here where we now have our axes A and B right there, where our max, or sigma max, goes along A and our sigma min goes along B. So now from this information that we have here, we know that our sigma average right here, our average stress, is equal to our sigma x plus sigma y over 2. So our sigma x plus our sigma y all over 2 is going to give us this sigma average value right there. And we know that our r is equal to the square root of our sigma x minus sigma y over 2 all squared plus our tau xy squared right there. So the square root of all of that will be our r value. Now we can obtain our principal stresses at A and B. So we can see there's A and B right there, which will correspond to our sigma max from our start point here over our origin right there, and our sigma min right here at B. So the distance from O to A is our sigma max, and the distance from O to B is our sigma min, and that's related by this equation right here. We see our sigma max and our sigma min are equal to our sigma average right there, plus or minus our R. So we have those two values up here. There's our sigma average. There's our R right there. So we can plug in. This is just all from our sigma x, our sigma y, and our tau xy right there. So we can plug those all in to get our values now for our sigma max and our sigma min. So now we can also see we have this relationship here, 7.12. And in 7.12, this is where we're looking at this down here, our 2 times our theta p information right there. So this is the tangent of 2 times theta p is equal to, where do we get that angle from? Well, 2 times our shearing stress right here, our tau xy, divided by sigma x minus sigma y. And the reason we want this here is we want to obtain everything from these information we have for our plane stress right here, our sigma x, our sigma y, and our tau xy right there. So we can relate this from equation 7.12. So now we have all the information from those 3 elements right there for our state of plane stress, sigma x, sigma y, and tau xy, to construct and draw out our Moore's circle. So let's go back to Moore's circle and really look at this and make sure we understand how we can utilize that information from our plane stress element up here, our sigma y, our sigma x, and our tau xy from this here, to actually draw out our Moore's circle. So we look at this here and we say, okay, well, I've got this point B and this point A here, and we know we can get our sigma max and our sigma min right there from this relationship that we see here, which relates back to our sigma average and our R value, which again relates back to all those individual components right there. So we can plug in our individual components to get our values here for sigma max and sigma min, or our 2 values for A and B outside of that there. So now we can also take a look here and say, well, what about our X and our y down here? Well, we get the angle of x and y right here from this relationship from 7.12 in our text. We can also see we can get the individual locations right here, our coordinates for this as well. Because if we look at x right here, it goes down a distance of tau xy. So this right here, our tau xy, we go down that distance to get there. So we go down on our tau axis, a distance of tau xy right there. Come over here, whatever that tau value corresponds with right there. And the same up here, we go up a value of our tau xy right here to get to our y like that there. So now we can also see as we come over from our center a distance of 1/2 of sigma x minus sigma y to get that location there. So our coordinates for our x are going to be sigma x right here, because we're just moving there, minus, comma, a negative tau xy right there, because we're going down below that axis. Whereas over here now we have a sigma y value right there, and we have a plus tau xy, because we're going up in our tau axis right there. So that's how we can get our coordinates for our x and our y on the circle right there. So now I want to move on to the discussion of Moore's circle for plane stress right here. So with Moore's circle uniquely defined, the state of stress for the other axial orientations may be depicted. So we come back over here to our diagram on the left here in part A. We have stress elements referenced to our XY axis and then transformed to obtain components in our X prime, Y prime axis. Now what we can notice is that for the state of stress at an angle theta, there's our angle theta right here, with respect to our standard XY axis, this is our standard XY axis right here, where we can see now we have, there's our sigma x going in our pure x direction, our sigma y going in our pure y direction right there. And we have our tau xy, which is also moving in our pure x direction right here, according to our xy coordinate system right there. So for our state of stress at that angle of theta right there, with respect to that xy axis, we can now construct a new diameter, an x prime y prime, that's going to be at an angle of 2 theta with respect to our xy. So our normal and shear stresses are obtained from our x prime y prime coordinate system. So going back to our diagram here in part A right there, we can see if we rotate this standard XY coordinate system for our stress element right there to these new X prime Y prime axes. We go down, we rotate it by this angle of theta right there. We come down here. Now we see there's our X prime and our Y prime coordinate system right there. Now we can see there's our sigma Y prime going in our Y prime coordinate direction and our sigma X prime going in our X prime new coordinate direction right there. And now we see we have our tau X prime Y prime right there on that stress element. So looking down here, we can see our corresponding Moore circle over here. We take a look at our axes, and again, we have our normal stress right here, our sigma on our x-axis right here, and our shear stress up here on our y-axis, our tau right there. So we have now, there's our standard diameter right here, our x, y right there, which we can see correlating back to our standard XY coordinate system right there. And as we said before, this new diameter is at an angle of 2 times theta with respect to XY. So there's that 2 theta with respect to XY. And we can see now each of these points right here from our X prime, Y prime diameter, that new diameter right there, we can correlate back to our sigma in our tau direction right there, and there's our sigma in our tau directions right there. Our coordinates for that there corresponding to our sigma and our tau coordinate systems, which we're using for Moore's circle shown in this diagram. So as we continue on with our discussion for Moore's circle for plane stress right here, let's take a look at Moore's circle for centric axial loading right here. So in part A, what we have here is a member under centric axial load. So you can see there's our load right there, the centric axial load right there, P, and our P prime right there. Now we can see our standard coordinate system we've drawn out here, our Y right there going up, and our X positive right there going to the right there. So now we have this element here that we can take a look at. How do we get to B, which is B is our Moore's circle, utilizing that member under centric axial loading? Well, we can see we have this relationship here that our sigma x is equal to our load over our area right there. And we also have the relationship that our sigma y is equal to our tau xy, and this is equal to 0 as well, which makes our sigma y equal to 0 as well, because if we look back at A right here, this is just a centric axial loading. There is no load, and what we specified as our y direction, the load is only in our x direction, which makes both of these terms go to the 0. So with that information, we come over to Moore's circle and B right there, and we say that our sigma x right here, which there's our diameter right there from x to y right there, is equal to that load over our area right there. Now in part C, what we have in this diagram is an element showing our planes of maximum shearing stress right there, where we have this relationship here that our sigma prime right here, as we go to this new axis right there, that in this case here is at 45 degrees, is equal to r, where r, if we come back here, this is our radius r right there on our circle, which is going to be half of our diameter right there. So this is equal to our tau max right there, which is our maximum shearing stress right there, which if we go back now right here, we can see that our maximum shearing stress is going to be related to P over 2A. Now, why is this P over 2A right there? Well, if we think about this in relationship to diameter and radius right here, if our full diameter from x to y is equal to our sigma x, which is P over A, and our r we've just said is half of that, our radius right there is half our diameter right there coming out there, and that's equal to our tau max, that's going to be our P over 2A, which would then just give us that relationship that our radius is going to be half of our diameter. So now continuing on to the discussion of Moore's circle for plane stress, let's look at now for a torsional loading, what Moore's circle would be for that there. So we can see down here in our diagram in part A, we have a member under torsional loading. So there's our torsional loading right there, our T and our T prime right there. See our standard coordinate system, X positive to the right, Y positive up going over there. Now we can see our T max on that element in the center right there. So for this here, we can now draw out our Moore's circle. So for Moore's circle, we can use the relationship that we see right here from these governing equations. Now, even looking back at A, we can see that our sigma x is equal to our sigma y, which is equal to 0. So we look over here, there is no sigma x, there is no sigma y. This is now under torsional loading here, no longer axial loading. So both of those, our sigma x and sigma y, are 0. But now we do have a tau xy here that's equal to t times c over j, where t is our torque, our torsional load right there, and we have our c, which is the distance to the outer surface from the center right there of our member right here, our round member right there, and this is over j, which is our polar moment of inertia. So for this relationship here, we can now come over to our graph for Moore's circle right there, where we can see again on our axes, our x-axis, our sigma, our principal stresses, our y-axis over here is our tau, our shear stresses right there, and we can now see there's our x, y going right up on our tau axis right there, and we can see now our tau max right here, our max shear stress equal to that relationship there, our tau times c over j right there, is our distance from our center up to this point y right here on our tau axis right there. So this is also the same as our radius right there. So our tau max, we can see from our Moore's circle right here, is equal to r. And that's also illustrated in our equation 7.18 from our textbook, where we have our r is equal to that tau times c over j right there. But now moving on to part C right here, where the elements showing our orientation of principal stresses right there. So we can see there's our orientation of our principal stresses right there, 45 degrees. There's our axis A, where there's our sigma max there, and axis B, where that's our sigma min right there. On that, according to our equation 7.18, the sigma max and min right here is equal to plus or minus r, which is plus or minus that radius. As we saw now, our radius right here is equal to our max shear stress, which is plus or minus now our t sub c, or t times c over our j. So our torsion times that distance to our outer surface all over our polar moment of inertia. So now let's take some of that theory and governing equations for Moore's circle and apply it to an example problem here. So let's take a look at concept application 7.2. Now this 7.2 is very similar to our 7.1. We have the same plane stress element that we saw in that example of 7.1 as well. And we can see this is our same values as well, our 10, 40, and 50 megapascals. And they tell us in this problem here that for a state of plane stress considered in that application 7.1, they want us to do now three things. So within these three things that we're going to do right here, we're going to have part A, this is a different part here, we're going to construct Moore's circle. Then we're going to use that in order to determine our principal stresses, and then in part C, determine our maximum shearing stresses and our corresponding normal stresses. So they're still asking us in B and C solve for similar things we did in our concept application 7.1. Difference now is at the beginning here for part A, we're going to construct Moore's circle in order to do that. So now let's actually begin our construction of Moore's circle utilizing this plane stress element right here. So from this plane stress element here, let's take a minute right here and write this out. It's going to make our lives a lot easier as we're going through our solution to clearly have these labeled. So we have our sigma sub x is equal to our 50 MPa, right from this here. We have our sigma sub y is equal to our negative 10 MPa right here, and that's going in our negative y direction, hence the negative sign there. And our tau xy is equal to 40 MPa right there. So that's all the information that we're going to need in order to create our Moore's circle right there. So now let's go back to our previous slides and come up with our governing equations where we have our average stress right there. Our sigma average is equal to our sigma x plus sigma y over 2, and our r value right there is a square root of our sigma x minus sigma y all over 2 squared right there, plus our tau xy squared right there. So we have all that information we can plug in to get those. So let's just deal with those two governing equations first. So with that there, we can say our sigma average right here, which is our sigma x plus sigma y over 2, which is equal to our sigma x is 50. Our sigma y is negative 10. Pay attention to that. So this is all over 2. So 50 minus 10 is 40 divided by 2 is 20. So now we have a value right here for our sigma average right here, which is 20. Now, next thing we want to do is come up with our value for our r. Our r is the square root of sigma x minus sigma y all over 2, quantity squared, plus our tau xy squared. We go back up here, plug those values in. We have the square root of 50 minus a negative, so double negative 10 all over 2, quantity squared, plus a 40 squared. Well, we look at this and we say 50 minus a negative 10 is 60, divided by 2 is 30. So 30 squared right there, plus 40 squared, take the square root of all that, we end up with a value for r of 50. Then the next thing we can do is we can say, well, our sigma max and sigma min are equal to that sigma average plus or minus our r value. So our max and min values right here, which are our min, and our max right there, which are points A and B on our Moore's circle, are now going to be equal to our sigma average plus or minus our r, where our sigma average right here we just found to be 20. And our r value we found to be 50. So plus or minus will give us our max and our min. So we have a minus of 30 and a min of 30 and a max of 70 right there, which correspond now to our points B and points A on our Mohr circle. So now that we've calculated out our values for our sigma average here of 20, our R of 50, and our sigma min and max of negative 30 and 70, let's go back over to our generic form here that we're using for Mohr circles. This is the same one that we used earlier in the lecture as well. So let's plug into this one for now, and we'll see, okay, our sigma min, that's a negative 30. Our sigma max, we put in a 70 right there. The first thing that we notice is this is not quite right, because our B would technically be over here and our negative right there for negative 30. Well, let's keep going with that. And the other thing that we know here is our distance from our origin right here to point C would be our sigma average right there, which would be a distance of 20 from there to there. So now we have positions for our A right out here, which is 70, our B, which is negative 30, and our C, which is 20 right there. So we have all of those values there. The next thing I want to take a look at is to come up with our theta sub P. So we have our general equation here that the tangent of 2 times our theta sub P is equal to 2 times our shear stress tau xy divided by our sigma x minus sigma y right there. So we'll plug into that general equation there. Well, our tau x right here is 40, so that was right there from our given problem right there. And we now, our denominator here, our sigma x, is given to us as 50. And our sigma y is a negative 10. Right there, we plug all those in. That's 80 over 60, 40 over 30, or 4 over 3. Rearrange this, and this is saying that now if we move this to the other side, 2 times our theta p is equal to the inverse tangent of 4/3. We do that out there, and 2 times our theta sub p is equal to 53.1 degrees. Divide both sides by 2, and now our theta sub p is equal to 26.6 degrees. So that plugs in right there. So now we have that information for our theta sub p value right there, our 26.6 degrees. So what I've done here now is I've put this into a whole new version of Mohr circle. So I started from scratch and drew this out here with all the information that we've calculated and gathered so far in this problem. So you can see down here I have my sigma max is 70. I have my sigma min of negative 30. And now you can see I have my axes in the right spot. I'm not using that general format that we saw from Mohr circle in the first couple slides. I've created one that is accurate to our values right here. So again, there's that sigma min right there. Now we also have our value for our sigma average, which right there comes from our origin to our point C. So that's 20 right there. So now we have all the information for A, B, and C points on Mohr circle right there. Now we also have our value for R. R is 50. We see that there's our R right there that we've drawn in there. We have, again, that theta sub P right there, so I put that in. That's my 26.6 degrees right there, and that was my calculation we did before for the negative 30 and 70 for the sigma max and min right there. Now we can also see over here, here's my tau xy. So my tau xy was given to me in the problem, and that's 40 megapascal, so I've included that there. Now what I don't know yet are the coordinates right here, my y, so that's my sigma y, and my tau xy, which I have, and I can plug those in. And I also have over here my x, which is my sigma x, and my negative tau xy. And then this distance down here from C to the point right there at x right there, which is 1/2 of sigma x minus sigma y. So I can come down here. Let's deal with that first. So I have 1/2 of sigma x minus sigma y. Well, my sigma x is 50 megapascals. My sigma y is negative 10 pascals right there. So 50 minus the negative 10 is the same as 50 plus 10, or 60 over 2, which is 30. So this value right here now is going to be replaced with 30. So we know that. Now our x, let's take a look at our x here. This is our sigma x, comma, our negative tau y right there. So our sigma x right here is 50 megapascals. So I can plug that in right there for my x component of that. And my negative tau y would be a negative 40. So this is going to be 50 comma 40 for my coordinates right here on my sigma tau axis for my Mohr circle right there. We do the same for y. Our y, we can see here, was a sigma y and a tau xy. So our sigma y right here is a value, we come up here, is negative 10 megapascals, and we have right here our tau xy right here is 40. So this is a negative 10, 40. So we go over on our sigma axis here, negative 10, and we go up here at value of 40 right there, and that gives us now our coordinates for our y. So now those three things that we didn't have for Mohr circles, we now have them all clearly labeled. We've defined these, we've done our calculations, and we can plug them in for those 3 yellow boxes. So that's exactly what I do there. Now I fill everything out right here in Mohr circle. So again, let's just go over all this. We have our sigma max of 70. We have our sigma min of 30 right there. We have this value right here of 20, which is our sigma average right there. We have our tau xy, which is 40 megapascals. We have this value down here, which is our sigma x minus sigma y over 2 of 30 right there. We have our angle right here of 26.6 degrees. We have our radius of 50 right there. And now we have our coordinates for x and y as well. So we have everything we need plugged in for Mohr circle at this point. So as we can see, there's a lot of different dimensions that were on that Mohr circle that we saw on the previous slide. There's different ways to calculate those values as well. The one way I went through in the most sense that followed the examples and the equations and theory that we did throughout this lecture and this module right here, but there are other ways that we can do this right here. So again, we have that sigma average right there was that 50 plus a negative 10 over 2, which is our 20 megapascals. And we can see that there's that value right there for our sigma average there. We can also do this by our labels right here. If C to F is equal right here, so C to F right here, well, this is equal to this distance right here from O to F minus this distance right here from O to C right there. So we can say that C to F is equal to 50 minus 20 right there, which is 30 right there. So that was another way to get that value right there, going from our center to point F right there of 30 megapascals there. Now we can do the same thing here for our F of X right there. So F of X right here is our tau sub X right there, and we can use that information as well. Now we could calculate our angle based off of a trig triangle right here. We could also do Pythagorean's theorem using our CX right there. So this is our CX right there is equal to now that square root now of the sum of the squares right there of our 30 squared and our 40 squared, which are our sides for that right triangle right there. So that's another way that we could get those values right there. And like I said, again, from that right there, that right triangle, and knowing all those sides, we could also back out that angle there as well for our theta sub p. So just another way to look through and solve some of those values. So let's look at some other alternative approaches to find our sigma max, our sigma min, and our theta right now. We already have these values calculated out, but let's just see if we had these visual representations here from Mohr circle and we had that information, how could we also calculate some other things? So for our sigma max, we're saying that this is from O to A right there. So if that's our sigma max right there, this is equal to OC and our CA. So our OC we have as 20. And our CA is our radius right there, which we know is 50 right there. So this goes from there to there. That's our radius. That's 50. So 20 plus 50 would give us that sigma max of 70 megapascals. Now we can do a similar thing for our sigma min over here. So our sigma min, we found this is O to B. So this is this distance right here. We already found this to be a negative 30 on our Mohr circle right there. But if we had this information from this one here, we can say OB is equal to our OC minus our BC. So there's our OC right there, and this is our BC right there. So if we subtract those there, we end up getting 20 minus 50 again, that radius right there, and this would give us a sigma min of negative 30 megapascals. So now that's how we get our sigma max and sigma min, looking at our values from our graph right there. We can also get them from, we can do the same thing now for our theta term. So we have this relationship right here that says tangent of 2 times our theta sub p is equal to, in this case here, it would be our fx over cf. So this is our fx, this is over cf, so this is just doing out our trig right there. Tangent is opposite over adjacent right there, so we can get back out that angle by saying, well, this is equal to 40, this is equal to 30, because our fx is 40 and our cf is 30 right there. So we can back that out. Now we can say that 2 times our theta sub p is equal to, when we do the inverse tangent of 4/3, is 51.3, and then we can divide both sides by 2, and our theta sub p is 26.6 degrees, and that was just getting our 30 and our 40 directly off of our Mohr circle. So now as we wrap up this problem right here, let's take a look at our stress element orientations for principal and maximum shear stress in this diagram here in part C. So we can see down here we have our XY coordinate system right there. There's our X, there's our positive Y. If we go up at this angle of theta sub P right here, now we can see there's our sigma max, which we found to be that 70 megapascals. This is our sigma min, which we found to be 30 megapascals right there on this new A, B coordinate system right here, which is up at that angle of theta sub p. Now if we went all the way up here to 45 degrees right there, then now we have this relationship over here where we have this new D, E coordinate system right there, and we can see there's our tau max right there of 50 megapascals. There is our sigma prime of 20 megapascals on both sides right there. So there is a visual right there from that figure right there showing those values now for sigma max, sigma min, and our tau max right there at different orientations for that element. So coming over now to our Mohr circle representation right here, this is used to determine our principal and maximum shearing right there, so we can take a look at all the information. So there's that sigma max that we saw there, there's our sigma min that we saw right there, and our tau max is going to be the max height right here on our tau axis right here, which is going to be that 50 right there. So we could grab all of that information directly from Mohr circle right there. The last bit of information we need down here is our sigma max, our max shear stress right here, our sigma sub s right here. So we can see our sigma sub s is equal to, we recall this relationship of sigma sub p plus this 45 degrees right there. So we have a value for that sigma So P already that we've calculated, add 45 to that, and what we end up with is our sigma sub s now is 71.6 degrees. Our tau max, again, is equal to that radius, and we've shown that right here in this diagram from Moore's circle right there. That's equal to 50 megapascals. And then we also have the relationship now that our sigma prime is equal to our sigma average. We already have a value for our sigma average, so our sigma prime is 20 megapascals right there, and that's that distance that we can see right here on Moore's circle.